Team US will report and will be challenged by Team Taiwan, and Switzerland will be reviewer. So I want to ask Taiwan to challenge the US to a problem.
I would like to oppose problem number 9, magnetic assist.
Okay, so problem number 9, magnetic assist is accepted.
对，就是主要是连接，因为这边是连接，对，然后你打好工作。
CSONGUF.
Whenever you're ready, you could start if you want to.
Okay, hello everyone, I'm from TNSA. I'm going to present the magnetic assist. So this problem is basically attack one or two magnets under a magnet pendulum and see how its motion affected by other relevant parameters, as you can see from the video. So basically when you release the moving magnet, it will jump between two magnets and finally your track oscillates around one of the magnets if there is two magnets in the case. And the relevant parameters we're gonna talking about, first of all, the number of magnets, obviously, 1 or 2. And the distance between magnets, we can vary it. And there are other parameters that I've considered, but I didn't do it in an experiment, which is the height of the pivot and the strength of the magnets. And there are some theoretical assumptions we made for the mathematical model, and most importantly, we regarded the magnets as magnetic dipoles. And also the strength length is not changing. Like it's not extensible. So we do the force analysis in order to get the equation of the motion. there are 4 forces. If there's 4 forces applied on the moving magnet if there's only one base magnet at x1, 0, 0. And there are gravitational force, magnetic force, drag force, and tension. So we're going to calculate them one by one. Regarding the magnetic force, since we suppose the magnets as magnetic dipoles, so the force between 2 dipoles could be expressed as this expression, and we simplified it into a constant over r to the fourth. And r is the distance between 2 center of the magnets, and the direction of the force is from one center to the other. And we have an experiment to test whether the model we use is correct. So we use electronic balance to measure the force between them, and we vary the distance between them and fit them in a line of a constant over to the force to test what the force is a constant over r to the fourth. And we fit the data in the line, and it fits pretty well, and we get the coefficient of the magnetic force by fitting the data. And the coefficient of determination is close to 1, so it fits pretty well. And so that we kind of proved the force between 2 magnets is a constant of r to the fourth, and we denote the distance between those 2 magnets as d, and the constant is gamma. And we project the 3 forces on x, y, z direction in order to furthermore put it in the equation of the motion. And also we also project the magnetic force along the string, which helps us to calculate the tension. So there are some other forces that are applied on the moving magnet, which is like gravitational forces, mg downward, and there's also a drag force, which we denote as a negative kg. And we, by doing an experiment, we are generating the damping coefficient, which is k. So we did a simple pendulum without any base magnets added, and we analyzed the data. We fit all the amplitude points into a curve, and then we get the damping coefficient k. So we can move on to the last force, which is the tension. We analyzed the forces along the string, which is the tension magnet. There's component of magnetic force and the component of gravitational force along the string. And as we know, the drag force is perpendicular to it, so we don't consider it at all. And since we know the net force along the string should be the centripetal force and b squared over L, so we could express tension by using that equation. And now we got all the forces we need. So we can move on to the equation of the motion. We use Newton's second law to divide all the forces over m along x direction, and we can get the equation of the motion, which is formed by 3 terms. The restoring term is basically, the restoring force, and the magnetic term, and the damping term. So same as x direction, y and z direction, they are all formed by those 3 terms. And the one of the case we talked about previously is only 1 magnet added, and if we add 2 magnets, we just do superposition, and it will look like this, and it's just 2 terms of magnetic terms added and nothing different about others, and it looks like this, which is still formed by these 3 terms. So we can move on to the experimental part. We made a wood stand which could hold the pendulum, and we used a angle gauge, 2 angle gauges here for the initial position, and we used a clip and a tripod to stabilize the release of the moving magnets, and we used a 60 frame per second phone to take videos here. And yeah, that's a real experimental setup, and this is it. And as you can see, we fixed a plastic clip on the tripod to release the moving magnets. So that's a kind of view of the video we take, and we put it in the tracker to analyze it in x and y direction. So what we got, one of them is the phase space, and we use phase space to describe the motion. So the phase space is defined as a plot of the position versus momentum, as well as the, you can also regard it as a position versus velocity, because mass doesn't change in our investigation. And for this one is the phase space for ideal simple pendulum, which means like when you move the x or y, when you move x or y, it will finally comes back to the same point with the same velocity, which means it's stable. Like there's no energy dissipated in the ideal pendulum. And if that pendulum is not ideal, the phase space is going to be looks like this, which is measured in the tracker. And as you can see, the radius of the trajectory is generally decreases, which means the energy dissipated during the as long as the time goes. And finally, it comes to the center of here, which means like there's a stable equilibrium at this point. So as we know what phase space is, we can use it to analyze our experiment. Our investigation. So this is the phase space for single magnets added at position 0, 0, 0. And as we can see, this one is the data we collected in the tracker, and this one is the MATLAB simulation we got from our mathematical model. And this you can see the matches pretty well, and as you can see, the energy dissipates along the time goes, and there's stable equilibrium at the center. And when we add the second magnets, they are like symmetrically distributed at, like, for example, they are at negative 9 centimeters and 9 centimeters along x-axis, and the phase space looks like this, and our mathematical model matches pretty well with the experiment data. As well as this, we even if we change the distance between magnets, the data matches pretty well. And another thing to indicate motion is the basin of attraction. So how to read the graph is that the position of each pixel is the initial position of the pendulum, and the color of it is the final position or the final basin of attraction that the pendulum falls into, which is the final base magnet it oscillates around. And blue is the left one, red is the right one. So we use experiment to measure the basin of attraction by measuring different initial positions and see the final positions. And it matches pretty well with the theoretical data, which you can see in the center part. There is a stable region inside, and as well as this. And in the outer layers, it's like ring shape, so it matches pretty well. And we vary some parameters, like the distance between two magnets, and as you can see, the stable area was stretched horizontally, and the area of it is generally changing, like increasing and then decreasing. And we also changed the height of the pivot, and as we can see, as the height of the pivot is higher, the moving magnet is further away from the base magnet, and the stable region is smaller. And we also changed magnetic strength. When the strength is higher, the stable region is bigger. And we also considered the fractal, like the cross section of the basin of the attraction graph, which shows how chaotic it is. So as you can see, we take a cross section along the y direction, and in the middle part, it was whole blue or whole red, which means when you change the initial position a little bit, it will change. The final position will change a lot. And as we go further away from the center, the color of it changes a lot. When you vary the initial position a little bit, the final position will completely changes from one base magnet to the other. So it's generally becoming chaotic in the outer layer. And same as the vertical cross section, as we know, as we can see, this one is taken in the kind of center of the plane. And when we move the cross section to the outer layer, it becomes more chaotic. So the basin of attraction is fractal. Yeah, and comes to our conclusion. when we increase the magnetic strength, the stable area is generally bigger. When we increase the height of the pivot, when we lift it up, the stable area is smaller. And when the distance between those two magnets increases, it kind of stretches the stable region horizontally. Yeah, and that's all I have, and those are the references.
Hey, thank you very much. Now, questions of the opponent.
Okay, so thank you for the report.
Yeah.
Okay, so in page 6, I can see that you use a type of estimation, right? So here you did not account for the orientation of the magnet, right? Because your model is assuming the parallel dipole.
No, that's not the same. It's just
You simplify. So in your calculation of the simulation, you all simplify to the r to the power of -4, right?
Yeah.
So that is the simplification for parallel.
Yes.
Okay. So for next question, in page 24, I see that you have calculated a velocity. So how did you calculate the velocity? How many point averages did you use?
Oh, you mean the velocity?
Yes, because you have the velocity plotted in space. So what is?
So the velocity is basically, so how the tracker work is that they track.
Oh, so you use the normal tracker
Yes,
setting,
that's
which is the
tracker.
2-point average.
Yes.
Okay. So do you have a trajectory graph of your motion?
Trajectory graph?
Well,
No, I don't.
in x, y. So okay, so I can't really see from this graph. So, but is the trajectory always linear, meaning that you will pass through the single magnet linearly, or you will turn or something like that?
No, I just pass it linearly.
So it will always be linearly throughout the whole motion, or will we turn or something?
No, if there's an initial velocity of it, it will turn around.
Okay.
If there's no.
Okay, turn to page 29. I can see that you have a basin of attraction with an somewhat experimental verification. Is the two sides symmetrical?
Yes, it is.
It's symmetrical. So do you done experiments for one side and assume the other, or?
No, I've done for both sides. And
Okay, you have also mentioned the chaos. Do you have a calculation of the Laguna experiment?
We calculated, but I didn't put it in the presentation. It's bigger than 0, which is the and this one.
Okay, so you have a proof of the sensitivity of the initial conditions. Okay, turn to page with the sample model. You have.
I don't think there's enough time left for this question.
Thank you.
ready for your presentation now.
Okay, good morning, dear viewers and debaters. I am Andrew Lee from Team Taiwan, going to be opposing on problem number 9, magnetic assist. So, for the problem statement, I think the key questions to this problem is, first of all, the equations of motion describing the system. So, the reporter have successfully modeled some forces that causes the motion. However, I don't think that they are totally complete, and we'll talk about later in the discussion. And the orientation of the pendulum magnet. Because when we think of the assist, we actually moves around, and the magnet will change in orientation, thus changing the dipole forces and the effects of the string conditions. Like because the problem statement had mentioned using a string to do the experiment, so I think that it will be important to investigate that. And some relevant parameters will include the number of magnets, which they have investigated in 1 or 2 cases. However, they don't have a very clear explanation on what is the difference and whether the chaos will exhibit in the one magnet's case or not. And the geometry of the magnets, they only investigated the distance between the magnets. However, I think there will be other geometrical configurations that make the problem more interesting. And the release conditions where they have investigated using the fractal Bason boundaries and the string length, which they have investigated theoretically. For the reporting overview, they discovered for the 2 magnets case, the motion moves around the 2 magnets and eventually stops near 1. And that is their justification of the use of the fractal basins. And for the 1 magnet case, they have drawn a phase space diagram that converges into a magnet. However, they do not have the trajectory measurements. Okay, so for the model, they use a dipole to calculate the force, which I don't think is quite correct under small distances due to it cannot consider the finite size. And it also cannot consider the orientation, as they actually have an equation that can consider the orientation, but they move on to use a more simplified model. And they did not have considered a velocity-dependent Lorentz force that will cause a side wave force due to a QVB, because there are 3 electrons moving in the magnet. And I think this will cause a flower motion when in a single magnet case, which I don't see in their trajectory. And for the observation, they use a phase space, and they have demonstrated an ideal pendulum and the damped pendulum where it spins inwards. And I think they are trying to justify that one magnet case is same as a pendulum moving towards a stable point. However, I don't think it is that simple. And the 2 magnets case, they have plotted another phase space trajectory in which they will fall into 1 attractor. However, we can discuss on whether a 3rd attractor might occur due to gravity. And they have also investigated a fractal basin with experimental and theoretical agreements. And they have other parameters, including the magnet height of pivot and magnet strength. And for the chaotic region, they have investigated the basis of the attractor under different parameters. So these are the discussion points where I want to discuss about the chaos, because the chaos actually has multiple dimensions, including x, y, z, and the orientation mu x, mu y, and mu z. So these multiple dimensions will influence how the chaos works, and the Lyapunov exponent, which will talk about the sensitivity to initial conditions and how the motion moves towards the fractal basins. And we'll also talk about the possible motion, including a circular motion, a flower motion, and transient motion with the 2 magnets case. And we'll talk about whether a linear motion will be possible in 1 magnet. And the velocity-dependent Lorentz force can be added into their theoretical, because I don't think that there are only like 3 forces. It is that simple. And we can also discuss about other parameters if they have actually done the experiment on that. So I think we can start with the discussion. Okay, so first, so I would still like to talk about, can you draw the trajectory of the movement of the moving magnet?
Yeah, sure. You mean which cases?
The single magnet case.
So if there is a single magnet and you release it from here, and it will like generally attracted by this.
So would you agree that because I can see that in your forces you have only considered the force, the attracting force, right? But if would you agree that if the magnet is moving due to this, like the another force pulling it inward, thus causing like a flower motion to occur.
We think the flower motion is caused because of the instability of release.
Do you have an observation of the flower motion?
Yes, I did.
Can I see your videos?
Sure, but I didn't put the one magnet video in my slide.
Okay, so
Sorry about that.
so you think that the flower motion is caused by the instability of the release?
Yes, we
Can you
think
explain
so.
further on how that works?
Yeah, sure. So if there's initial acceleration when you release it, this is the base magnet, and if there's initial small, even if a very small initial velocity, it will goes round like this. Because there's a track force when magnet moves to here this way, right?
Well, yes. So I think this is the assist, which the problem statement has been mentioned about. Because if you
Yes.
traditionally think of like a gravitational assist, it is when a spacecraft is like flying through a space with a gravitational object, it can turn and have an
Yes,
increasing speed, right?
Yeah, that's.
But can I see your method of release? I don't think that this is actually the case. What is your method of release? Can you show
I'm
me?
using a plastic clip, and when you
Yes, I don't think that this will cause an initial velocity. And I can see from your phase-space diagrams that there is actually, the initial velocity is actually 0. So can you, is this a video or can you?
so the video is this also. Yeah, this.
Oh, you don't have the video. Oh,
Yeah, I don't.
it's, but I believe that it will not have caused a velocity right here.
But
Because if you
I
track,
think that's.
can I see your phase-space diagram in the one mechanism case?
Yeah.
Yes,
There
because
is a small initial velocity.
you use a 2-point average, so of course there will be an initial velocity, but I think it is very small, and I don't think it is what is causing this phenomenon to occur. Because
That's where I kind of disagree.
okay, so if it has an initial zero velocity, can you get the force? The force, if you only consider this, you will not have moved towards this thing, but rather will move towards the magnet. And the flower motion will not have gotten bigger, but rather converge into the, if you like plot a potential here, you'll converge into the here.
Yeah, the motion is convergence into here, right?
But have you observed that the flower motion will actually turn like 360 degrees? That
Because
like
you
like
need
this.
time for it to decay, right?
Yes, of course it needs time to decay.
Yeah, because there's initial velocity and it naturally turns it around 360 degrees.
Okay, so I still think that this velocity dependent Lorentz force needs to be considered, so that you have like a force and will enter it, so it will turn. Okay, so next we can move on to the space. Do you have the space for the z direction?
No, I don't. Because since in our video it's only attracted by, like there is only x and y direction in the video, so we didn't take a video.
Okay, so I think you have, in your theory, you have assumed that the string length doesn't change, right?
Yes.
So I think you can calculate a z direction by using the
Another
Pythagoras curve.
video?
No, using the Pythagoras curve because you knew that the L is constant, so you can
okay.
get the z
Oh,
direction.
that's a good idea.
Yes. Okay. So if you like draw a z phase space, what do you think it will look like?
I think it would look so. I think it will look like probably similar with the y direction, and only the side that y is bigger than 0.
Well, I think that if you have like a z direction, the phase space will be like pulled by the
Yeah,
gravity
like kind of
because
shifted.
it's because the gravity will like shift towards here.
Yes,
and
yes.
your conversion. I think it will be pulled by the gravity. So I think that the gravity may be a bird attractor in this situation.
Oh, sorry, the gravity.
A gravity might consist of bird attractor if you do it with the two magnets, because you can observe like the gravity might be dominant if the magnet distance is too large.
Oh, yeah. probably falls in between there, like
Yes.
between two.
Well, between. Have you done experiments on that?
No, I didn't.
Okay, so can I?
Since
So
the,
what do you think? Do you think the single magnet case will constitute chaos?
No, I don't think so. Because it finally falls into the same end position.
Okay, so yes, this I agree with you because it is not infinite time scale and you have a final position. But if the two magnets, can I see the fractal basis of the?
Yeah, sure. On fractal basis?
Yes.
How do
I want this page. Okay, so I can see with this page you're trying to do the experiments with the.
experimentally.
Can you explain further?
Yeah, sure. So we investigate different initial position and see which magnet, which base of attraction it finally falls into. If it falls into the left one, we color it in blue, and if it falls to the right one, we color it in red. And we kind of did several trials for those points and predicted with the color.
So you so you don't do experiments for these 2 points.
No, because I think that's because it's very close to the center, so I think it's symmetric. But other points that I chose here are all what I experimented.
Okay, so can I turn to the page where you have the experimental prediction, theoretical prediction with the.
Theoretical prediction.
You have a theoretical prediction with the double magnets case of the phase space, because I can see you have the phase space for the double magnets case.
Yes. Theory.
Yes, this is phase. Yes. Okay, so you have drawn. I can see from your experimental data that there is like this, and you can like somehow correlate with this graph. But I don't think the magnitudes match because like this maximum is like 0.8 meters per second, and this is like 0.4 meters per second. Yes. So do you think maybe your magnet is not your magnetic model is not working because I think there is a underestimation of how big the velocity should be. So can I ask what is the parameter in this setup? Is the distance between the magnets?
You mean the changing parameters?
No, this
Oh, the
for this
distance
experiment the
between
parameters.
magnets. This one is 0.0. Oh, 0.09 meters. So for this is the center, right? This position is 0.0.
I
this
mean
magnet
the
is
distance between the.
Oh, it's 18 centimeters.
Oh, this distance and this distance.
Oh, this distance?
Yes.
So it's 45 minus, which is 7.5. Yeah.
Oh, so it
So
is
it's 0.5
so
centimeters.
at 7.5 centimeters, can I see your prediction with the dipole model, the dipole characterization?
Oh, dipole characterization? What?
You have characterized the dipole. You have characterized that.
What do you mean the dipoles? Like
Yes, this, the next.
this one, okay.
Okay, this is the force to the distance, right?
Yes.
So this, so 7.5 centimeters, it should fall between the range of this and this because it has a greater distance, right?
Yes, that's right. There's somewhere here. 7.5.
So do you think the magnitude? So I think that from this graph you can know that the magnitude of the force is correct, but the prediction is not correct, and it has like 2 times the velocity. Because I can see that.
That's not as bad as 2 times, I think.
I can see
There's
some
Okay,
severe
thank you very
unpredictability.
much. I would ask the opponent now to summarize the discussion, please.
Okay, so for the summarization of the discussion, we have discussed the motion of the pendulum. We have discussed the motion of the pendulum magnet, and we have also talked about the flower motion, which they did not have investigated. But I think it is a pretty important part of the phenomenon. And we have also investigated the gravity, which may be an additional attractor. So because they did not plot the z phase space of the single magnets, if they have plotted, it would have seen like if you have the 2 magnets, there will be like also a new attractor under certain configurations of the potential fields. And we also have investigated the magnitude of the velocity between the experiment and the theory. And we have also clarified, and they have using assume a line dipole, which I think that it is not correct, and they should have used their better equations to account for the orientation of the magnet. And also we have also talked about the Lorentz force, which may cause by the velocity difference. A lateral force might be present, so we will spin the magnet up.
Thank you very much.
And that would be my.
Sorry.
Thank you.
So now I will ask the reviewer to ask questions, please.
Thank you very much to both of you. Opponent, please. To the reporter, you mentioned the magnetic force is a relevant parameter.
Yeah.
Did you vary the magnetic force?
I did in the simulation, but not in the experiment.
Not in experiments. Okay, thank you. Could you please go to slide 70
7.
with the approximation?
Yeah.
Oh, I'm sorry, then I might be mistaken. The next, no, with the theory where you have r to the power of 4. Yes.
You mean? Oh, sorry.
Yeah. No.
Oh,
Please.
you mean the equation?
With your theory where you have constant over the power of r to the 4 on the right in the red.
Here.
With your theory of the magnetic force. Okay,
This
and
one.
meanwhile, yes, this one. How do you justify that the term is constant? Which term is constant?
This whole term, because it's only based on the magnetic dipole moment of two.
Do you not think it depends on the radius?
Because we're not
on
taking the
R?
radius.
And do you not think it depends
Oh,
on
the
R?
R? No, the
Okay, thank you very much. That's all. To the opponent, I'm sorry, we have to move on. To the opponent, what effect do you think the Lorentz force has? You mentioned that in your opposition.
Because the Lorentz force is that QVB, so it will depend on the speed of the magnet, which will depend on the process of the magnet.
Okay,
and it is what causing the sensitivity to initial conditions in this phenomenon.
Okay, what
it also causes
I'm sorry, I'm sorry. What does the Lorentz force act on? What does
it acts on the magnet, which
Okay,
is
thank
a
you, that's
lateral
all.
force.
Thank you. You mentioned that the gravity has an effect on the phase space. Do you
Yes.
think it also has got also an effect on the XY phase space?
I think that it will happen. Wouldn't have an effect because it is already considered in the equations of motion. But for the z
Well, if it is considered in the equations of motion, wouldn't it have an effect?
but for the phase space, it would not change the
Okay,
initial
the
conditions.
sense-
However, if they change the phase magnet
I
position,
think that's.
it will be
I'm
an
sorry, we don't
effect.
have the time. I'm very sorry. Could you, the reporter, please go to the slide where you have slide 17. You said you have the gravity term on the bottom only at z, g. Yes. Do you think the gravity has only got an effect on the z component?
So the gravity
Yes or
only
no
has a
question?
direct
I'm sorry.
effect on the direction, but there are some gravity terms in the tension. So
Yes or
there's
no?
not
Does the
direct-
gravity only have an effect on the z component?
if you say gravity force, yes.
Yes. Okay. Thank you. Could you please go to slide 16?
Yeah.
Is this slide 16?
Yeah.
Okay. What was fitted exactly? I'm sorry. What was fitted? Which terms were fitted?
The gamma, this constant.
Only
and
gamma.
the K.
Gamma and K.
Yeah.
Okay. Thank you.
Short
I think that's all. Thank you very much.
Thank you.
Thank you. Now you got time for preparation.
Hi and welcome to my review of problem number 9, magnetic assist. So the problem statement was already read. I think the most important points are once again to investigate the motion and to identify the relevant parameters and investigate what effect they have on the motion. So for the outline of the report, I really liked your setup. First, I really like that you have a controlled mechanism to release the magnet. However, I really think that the qualitative explanation and the types of motion, you did not go into that. I would have liked that. I'll get back to that later. The report, yes, I like the controlled release mechanism. I think that was really good. You also had a simulation of the basins of attraction that was really good, and you varied some relevant parameters. However, the big points are you did not investigate the types of motion that the magnets can have. I think that's one of the main points that should have been investigated here. I think you only considered planar motion. However, if you give the magnets an initial velocity, they could also show circular motion, where they go in circles around the magnet. You also mentioned that the magnetic force was a relevant parameter. However, you did not vary that in your experiments. You also did not have a good enough qualitative explanation, in my opinion. That ties back to the equations of motion. To the opponent's speech summary, I think you first criticized this equation of motion and stated that was insufficient. We agree, and we think that the assumptions were not justified, and the simplification with the constant divided by r to the power of 4 is not valid, as the constant term still has an r vector in there, which is not, you cannot simplify that. The opponent also pointed out the missing parameters regarding the geometry and the trajectories, and we agree with the opponent because the relevant parameters were not investigated. Only one magnet was looked at, and there was a lacking investigation of the different types of motion. The opponent also criticized the dipole model. We disagree there. He criticized the dipole model and mentioned the Lorentz force. We agree that, we agree the eddy current should have been investigated. The opposition, he pointed out that the trajectory plots were missing. We agree with that. It was very good. He mentioned that 3 equilibrium states should have been also investigated, and he also pointed out that some assumptions were not justified with the simplification of the theoretical model. However, he did not criticize the comparison between theory and experiments. I think that should have been done. And also, there was a clear misconception about the Lorentz force. When I asked him on what does the Lorentz force act on, he stated it acts on the magnet, which is not true, because the Lorentz force acts on charged particles, which are the electrons in the magnet. The magnetic force, it could have induced eddy currents in the magnets. That should have been investigated, because the eddy currents can form a magnetic field, and that can interact with the magnets. And I would have also liked that he stated his opinion a few more times. Now to the discussion topics. The trajectory you discussed the trajectory of a single magnet and the flower motion. The reporter stated that the instability is mostly due to the release conditions. The opponent stated that the eddy currents lead to the flower motion, and the release mechanism was good. In our opinion, the main point why these flower patterns form are definitely the release mechanism. However, the reporter should have definitely investigated the eddy currents. As mentioned before, these can get induced in the magnets and produce a magnetic field which can impact the motion of the upper magnet. And you also talked about the fractals of the basins of attraction. The reporter said that they determined it experimentally too, also determined it experimentally, and the opponent stated that you were at some missing points in the vicinity of the magnet. We agree with the reporter that this is not very relevant, as it is very clear that the magnet would go to the closest magnet if it's so close to that magnet. Okay. Thank you very much for your attention.
Thank you. So now, the concluding remarks of the reporter, please.
Okay, so thank you for the reviewer and opponent, and I think that's a great discussion about this problem. And there's something that I want to clarify. So first of all, the reviewer mentioned that in this concept there are still R terms, but actually the R terms means the direction of R, which is irrelevant to the number of R. So it's just stating the direction of the force, which is not relevant to the magnitude of the force. So we in my opinion, we could use a constant to replace it. And for the Lorentz force, I think that's a good idea to investigate it. But I still think the main cause of the flower shape is because of the instability of release. But that's a very good idea to consider the eddy current in the investigation. And that's a very good thing that I will further investigate. And for the trajectory is missing. I think we could use the phase space to kind of describe the motion. So it's good to include it, but I think it's fine with this. Yeah, and all right, and that's a very interesting discussion with you guys, and I got some further direction of investigation, and thank you for all.
Thank you very much. Now we got some time for questions from the jury. Yes, please.
Question to the reporter. What solver did you use to solve your equations of motion?
Oh, you mean how to integrate it?
Yeah, like
Euler's method.
okay.
Right, you can map it.
Okay.
Yes.
To the reporter, the name of the problem is magnetic axis.
Yeah.
How does this axis the motion?
I think it kind of gives it a it attracts it to the magnet.
Okay, thank you.
But,
To the opponent, the same question. Any idea?
Well, I think that it is because when you move the magnet, a velocity-dependent force, which caused by the jet velocity of the magnet, will constitute a shifting force like this, and thus will cause the velocity to like increase with the magnetic force.
Thank you.
Any more questions?
I have a question.
Yeah.
The reporter on slide number 30.
30.
Yes. So here on the measured graph, we can see that you filled out the background.
Oh, you mean this?
Yes, and on what grounds did you choose to fill it out like that?
So basically because in this field it's basically all red, so that just use red to fill it, but I think the more important thing is the data the points we point there.
Yeah, okay.
I have an add-on question to this slide. So on the left side, you can see near the y-axis that the red area goes up quite wide, quite far, and on the right, you have a perfect circle. Do you have any explanation for this mismatch somehow? So you want to compare those two, right?
Yeah. So,
you know what I mean. Okay, so that. I think it's not a short question anymore. Here we have a red area touching the y-axis, and here it is missing a blue area. Sorry, why?
I can show you when the strength of the magnet increases. There are some area here that is
okay.
color.
So,
probably because of the precision, it's not shown in the.
Okay. Yes, please.
Yeah, question for the reporter. What's the main cause for damping in your model?
It's air friction.
Drag?
Yeah, drag force.
What do you think the opponent?
Yes, it is drag. The viscous force is proportional to V.
Yes, please.
Question to the opponent. I believe you introduced the gravitation attraction point. And is it a stable point of attraction or an unstable point of attraction?
I think if you like increase the length of this distance between the magnet, there will be a new stable point of the gravity at the bottom position.
Okay.
To the opponent, you mentioned about the Lorentz force and the Leavitt
said that it's only act on the electron causing the eddy current. Do you have anything to defend yourself?
Okay, I to clarify that I did not say that eddy current is the cause of the electron. I think it's because if you like model the packet as like a surface current, it will have a electron drift velocity. It is not dependent on the eddy current. Thus, it's like 2 orders of magnitude bigger than eddy current. Thus, I think it is significant in this phenomenon.
So one question to the reviewer. You were not so happy with the opponent saying the eddy currents are acting on the magnet. So what do you mean?
My problem was that I asked him clearly that what the Lorentz force acts on,
Yeah.
and he stated that the Lorentz force acts on the magnet, and the Lorentz that is not true because the Lorentz force acts on charged particles, and the Lorentz force through the Lorentz force the electrons get accelerated, and that they form a magnetic field, and that is what interacts with the magnet, and that is the point that I wanted to get across.
To the opponent again, can the flower pattern of motion occur without the Lorentz force?
No, because if there is only attracting force, it will be linear. So it will like move towards the center, and it will be like always one line. Lateral force will be needed to drift the magnet.
Thank you.
Okay, thank you very much. ready? Okay. So then we continue on to grading. First of all, the grades for the reporter, please. We got 3, 4, 4, 4, and 4. Grades for the opponent are 6, 7, 7, 8, and 6. And for the review, we got 7, 7, 6, 6, and 7. Okay, so for the report we have. I already forgot it. I think it was was 4. No, 3. Was that 3? Right? Yeah. Could you comment on your 3 first, please, on the lower side?
Well, it's mostly about the content again. The overall presentation is good, and for the theory, I'm not convinced that the theory that you use is correct. But I mean the simulation part is quite convincing. But I mean the theory that you show is, I think, is kind of like disqualified by the opponent and the reviewer, that is not that reliable. And I think that about the approximation that you discussed with the opponent about the vector approximation that we approximate to the constant divided by r to the quadratic term, I don't buy that. Well, for the relevant experiment, I think that the data presentation for the attraction of basis of attraction is not that good presented because of this hand drawing, and I question its reliability. And for the on contribution and task fulfillment, I give you average score, and I deduct you a little bit for the jurisdiction. Yeah. So the partial point is 1 plus 1.75 plus 2.5, 0.5 and minus 0.5. So I round it up to 3.
Thank you. And on the higher side, do we have a 5? Or no. So one of the 4s may comment on that?
Yeah,
Please.
I think that I really appreciated your phenomenal explanation, the process that you found for the problem. But yeah, the presentation probably lacks of some precision in the scientific communication, especially for how your data were presented and how you try to match your data with your theoretical predictions. Yeah, then I subtracted some points from the question from the viewers. I think that in a simple pendulum, especially if you have not a way to lower the friction at the point where your string is hung, then that is because of dumping, not drag in air. So the term may be not relevant in your equation, but we found it from the top. Yes.
Okay, thank you. So for the opposition, we have on the higher side an 8, I think. Yeah. Would you like to comment on that?
Yes, so I really liked the question. I think it was very, very well done. For the questions, I gave a 1.5 because you almost asked all the questions I had at the moment. In the speech, I liked the speech quite a lot. I gave around 3 points for that. Although I believe your time management was not the best, you finished a bit early. And I like when you really have 4 minutes, and that's not a lot of time to tell everything that you want. So, but I quite liked the speech. And the discussion, I gave 2.5 points because I believe the topics you raised were very, very good, and your opinions on the topics raised were really good. But I felt that you didn't really bring in the jury into this discussion. You were mostly faced to the reporter or to the screen, and that way it was a bit harder to feel engaged in the discussion. And I believe that was missing for me to give an even higher score. But 8 I think is a very, very good score for the opposition.
Thank you. And on the lower side, we got a 6, I think. Is that correct?
Yes, you did.
2 6s. Where's the second 6? Okay. So you already comment. Maybe I will comment now. Overall, I also liked the questions at the beginning. and I also like the opposition speech quite well, so my grades are 1.25 for the questions and 2.5 for the speech. I didn't like the discussion that much because, in my opinion, the more interesting points were brought up at the end of the discussion, so the prioritization was not so good for me, and I also subjected a little bit due to the jury questions because I'm not so convinced that the eddy currents are completely necessary for the. But maybe I'm wrong. I don't know. We can discuss later. Yeah, and so I ended up with 6 because I got 2.5 for the speech and 2 for the discussion and 0.5. So correctly. You want to add something?
No, it's just exact to me. Like
Okay.
just,
Great.
same comment.
Thank you. Then for the review, we got. I don't remember. Where's the lower grade?
3 7s and 2 6s.
3 7s. Okay. Any 7 wants to comment?
Sure. I
Yes,
think
please.
that you had a good understanding of the presentation, both of the report and the opposition. Yeah, there was just this misunderstanding on the eddy current. The opponent said clearly when speaking that he was referring to the current and not to the magnet at the beginning. I mean, but except for this, it was well done conducted.
Okay. So, and for the lower end, for the 6s, anyone wants to comment on that? Yes, please.
Yeah. So I like the questions at the start. Again, for me, the review of the report and the opposition was good, but especially in the report, I would like to see a better prioritization from the pros and cons that you mentioned. The discussion analysis was good. Yeah, overall it was a good review, I think.
Okay. Thank you very much. Does any one of the teams want more clarification to any marks? Any grades? No? Okay, thank you very much. Thank you for this. So, before we are leaving, I would like to remind you that you are invited to give feedback to the jurors, and don't forget about that. And don't forget about giving the PDF presentations to the FAT assistants before you leave here. Thank you very much.